In November 2023, a spacecraft more than 24 billion kilometers from Earth started speaking in a language nobody on this planet recognized. The signal was still arriving. The frequency was correct. The strength was consistent with the expected loss over that impossible distance. The antenna was pointing directly at the solar system's core. By every technical measure available to the engineers at NASA's Jet Propulsion Laboratory, Voyager 1 was alive. And yet what it was transmitting made no sense. Instead of the neat, organized streams of science and engineering data the team had been reading since the Carter administration, what arrived at the Deep Space Network's receiving dish in Canberra, Australia, was a loop. Zeros and the number 377, repeating endlessly. The spacecraft was transmitting. It just was not saying anything. That contrast deserves a moment. When spacecraft fail, they usually go quiet. The transmitter cuts out, or the antenna drifts, or the signal drops below the threshold of detectability, and the mission ends not with a dramatic breakdown, but with an anticlimactic silence. Voyager 1 did none of that. Its radio was fine. Its pointing was fine. It was listening to Earth's commands and acknowledging them. Something had gone wrong, not in the spacecraft's ability to communicate, but in its ability to say anything worth communicating. The phone line was open. The voice on the other end had forgotten how to speak. To understand why this matters, and why it took 5 months to fix, you need to understand what Voyager 1 actually is, where it has been, and what it has been doing out there for nearly 5 decades. Voyager 1 launched on September 5, 1977. 17 days after its twin, Voyager 2, both spacecraft were designed as a one-time opportunity, a rare alignment of the outer planets, occurring once every 175 years, meant that a single spacecraft could use Jupiter's gravity to slingshot itself towards Saturn, and then use Saturn to continue outward. The window was narrow. NASA took it. The original mission plan called for encounters with Jupiter and Saturn, after which the spacecraft were expected to drift into retirement. Their useful science life finished. Jupiter came for Voyager 1 in March 1979, Saturn in November 1980. At each encounter, the spacecraft's instruments captured data nobody had ever seen before. Volcanic activity on Io, the detailed structure of Saturn's rings, the thin atmosphere of Titan. Then the planetary encounters were over, and the spacecraft just kept going. It had no more scheduled appointments. Nobody had made plans for what it would do after Saturn. What it did was keep flying. By the time it became clear in the 1990s that Voyager 1 might actually survive long enough to reach the edge of the solar system, the mission had transformed into something its designers had not imagined. Not a planetary flyby mission, but an interstellar precursor, a probe moving toward a boundary that no human-built object had ever crossed. That boundary is called the Heliopause. The Heliopause is the place where the solar wind stops. The sun continuously blows outward in all directions, sending a constant stream of charged particles, a mix of protons and electrons, flowing at speeds of several hundred kilometers per second. That stream, called the solar wind, inflates a giant magnetic bubble around the solar system. Inside that bubble, the sun's influence dominates. Everything in the bubble, every planet, every comet, every asteroid, the entire region we call the solar system, is inside this structure. Outside the bubble, the galaxy takes over. The boundary between those two domains is not sharp. There is a transition region. First, as you move outward, the solar wind slows to subsonic speeds and piles up, a region called the Helios heath. Then, at the heliopause, it stops pushing against the interstellar medium entirely. The interstellar medium is the material between the stars, and it has its own pressure, its own magnetic field, its own structure. Where the outward push of the solar wind and the inward pressure of the interstellar medium reach equilibrium, that is the heliopause. It is, in a practical sense, the outer membrane of our solar system. Voyager 1 crossed it in August 2012, the first human object to do so. The crossing was confirmed not by a single dramatic reading, but by a series of converging measurements. The density of the surrounding plasma changed. The magnetic field direction shifted. The cosmic ray counts from outside the solar system jumped. The team debated for months exactly how to interpret the data because the crossing had not looked exactly like their models predicted. Eventually, the evidence was overwhelming. Voyager 1 was on the other side. It was in interstellar space. Out there, the physics is different. The plasma is thinner, denser in some regions than others, and structured in ways nobody had ever been able to measure directly, because no spacecraft had ever been close enough to sample it. Voyager 1 was now sampling it continuously, simply by flying through it. One of the instruments still operating on the spacecraft at the time of the crossing was the plasma wave subsystem. It consists of two antennas extending outward from the spacecraft's frame in a wide V shape. When charged particles in the surrounding medium oscillate, they create weak electric fields. Those fields induce tiny voltages in the antennas. The plasma wave subsystem measures those voltages and converts them into data. What it effectively does is record the acoustic equivalent of the plasma, the way the medium is vibrating around the spacecraft at any given moment. Scientists can take those recordings and convert them to audio. The result sounds like a faint hiss, something between white noise and the static of an untuned radio. It is the actual sound of the space the spacecraft is moving through, not a metaphor. A literal measurement of the electromagnetic oscillations in the interstellar medium, converted to a form human hearing can perceive. For the first 5 years after the crossing, the plasma wave subsystem recorded data mostly in bursts. The interstellar medium surrounding Voyager 1 was, for most of that time, too thin and too quiet to produce a signal above the instrument's detection floor. What broke through were the shocks. Periodically, the sun releases a coronal mass ejection, an enormous burst of magnetized plasma that travels outward through the solar system at millions of kilometers per hour. These events, when powerful enough, eventually reach Voyager 1's position and slam into the interstellar plasma around it. The collision sets the medium ringing. Particles oscillate. The plasma wave subsystem picks them up and records a clear, strong signal for hours or days. And then the ringing fades and the data goes quiet again. James Cordes, a senior astronomer at Cornell University, described these events as a thunderstorm. The shocks were the lightning. Dramatic, brief, informative. Each one told the team something about where the spacecraft was, what the medium around it was made of, how dense it was at that particular moment. The science was real and valuable, but between the shocks, the assumption was that there was simply nothing to hear. The medium was too thin. The oscillations were too faint. The absence of a signal, scientists assumed, meant the absence of a phenomenon. This is an assumption with a very poor track record in astrophysics. Before LIGO detected gravitational waves in 2015, the conventional view was that no earthbound instrument was sensitive enough to hear them. Before the first underground neutrino detectors were built in the 1960s, many physicists doubted whether the particles could be measured at all. The history of astronomy is substantially a history of lowering detection thresholds and finding that the universe was talking at frequencies nobody had thought to tune to. The interstellar medium, in this respect, was following an old pattern. Stella Ocker was a graduate student in astronomy at Cornell University when she started going through the plasma wave subsystem data from Voyager 1 in detail. She was not chasing a specific hypothesis. She was doing systematic archival work, going through the years of recordings accumulated since the Heliopause crossing, paying attention to the intervals between the loud events that everyone else had focused on. What she found was a signal, a narrow band emission at a single frequency, very weak, very stable, continuous. It did not flare up during solar shocks. It did not pulse or vary with the spacecraft's position. It was simply present in the data from 2017 onward, steady hour after hour, sitting below the noise floor of casual inspection, but clearly above it when you looked carefully enough. The quiet parts of the archive were not quiet. They had just never been listened to at the right sensitivity. The paper was published in Nature Astronomy on May 10, 2021, with Ocker as lead author and Cordes as senior author. Ocker described the discovery in simple language, the faint, persistent hum of interstellar gas. That was it, not a spectacular outburst, not a dramatic anomaly, a hum, continuous, faint, and everywhere in the data once you knew to look for it. Cordes updated his thunderstorm analogy. The shocks were still the lightning, but Ocker had found the rain. The rain had been falling the whole time. The instruments had been recording it continuously. Nobody had separated the sound of the rain from the silence of the surrounding archive. The scientific value of the persistent hum was not immediately obvious from a simple description. To understand why it mattered, consider what the hum allowed scientists to do that the shock measurements could not. A shock event is a single data point in time. It tells you what the plasma density was at one moment when the shock arrived, and then it is gone. The persistent hum, because it is always present, allows density measurements to be made continuously over extended distances as the spacecraft moves. In practical terms, It enabled the team to sample the density of the interstellar medium at intervals of roughly 3% of an astronomical unit, where 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. At that resolution, measurements could be taken at intervals of about 4.5 million kilometers. Fine enough to see structure, fine enough to see turbulence, fine enough to detect gradients and density variations that no previous measurement technique could resolve. What emerged from those measurements was that the interstellar medium was not smooth. It had texture. The space between the stars was not a uniform thin gas stretched evenly between stellar systems. It had eddies, it had fluctuations, it had concentrations and voids at small scales that nobody had been able to see because nobody had ever been in a position to measure them directly before. Voyager 1 was moving through a structured medium, and the plasma wave subsystem was mapping that structure in real time, one faint vibration at a time. For a few years after the paper's publication, this was the Voyager 1 story. The spacecraft was doing science nobody expected it to do. It was listening to the universe at a distance and sensitivity no other instrument had achieved. The plasma hum was building up a picture of interstellar space that no telescope, no model, no indirect measurement could provide. Then, in November 2023, the machine doing the listening stopped making sense. The flight data subsystem was the heart of Voyager 1's communications. Every Voyager-class spacecraft carried 3 redundant computers designed to keep the mission operational if any single component failed. One computer handled the spacecraft's attitude and pointing, keeping the antenna aimed at Earth with a precision maintained over billions of kilometers. One handled commands received from Earth. The third, the flight data subsystem, had a job the others could not do. It collected everything: the readings from each science instrument, the engineering telemetry reporting the spacecraft's own health, its temperatures, its power levels, the state of each subsystem. It assembled all of that into a structured data stream and handed that stream to the radio transmitter for the broadcast home. Without the flight data subsystem functioning correctly, the rest of the spacecraft could be working perfectly, and nobody on Earth would know. The failure manifested as a loop. Instead of formatted telemetry, the spacecraft was repeating a sequence of zeros and the value 377 in a continuous cycle. The signal strength was fine. The carrier wave was intact. The spacecraft was still receiving and acknowledging commands. But the data channel was outputting garbage, and the team at JPL had no direct way to look inside the machine and find out why. The diagnosis was constrained by a physics problem that has no workaround. At 24.1 billion kilometers, a radio signal traveling at the speed of light, which is the fastest anything in the known universe can travel, takes 22.5 hours to reach Voyager 1. A response from the spacecraft takes another 22.5 hours to return. The round trip is 45 hours. Send a diagnostic command on Monday morning, and you wait until Wednesday morning to find out what it produced. If the command was wrong, you have lost 2 days and the situation may be worse than before. If it was right, you need to send the next command. Wait another 45 hours, assess the result, and repeat. This is not a communications inconvenience. It is a fundamental constraint on how engineering can be done at that distance. Every decision has to be correct or at least recoverable on the first attempt, because the cost of each error is measured in days. There is no rapid iteration. There is no quick fix and check. There is careful hypothesis, careful command construction, a 45-hour wait, and then careful interpretation of whatever comes back. The team decided to try something simple first. They sent the flight data subsystem a command to stop its loop and output the entire contents of its own memory. Not just the formatted telemetry it was supposed to produce, but every byte it was holding, raw, in whatever order it happened to be stored. The informal name for this command inside the team was a poke. The technical description was a directive to perform a full memory readout. The purpose was to compare what the FDS was actually holding against what it was supposed to be holding, according to the original design documents from the 1970s. The theory was that the discrepancy between the two would tell them where the failure was. The poke went out on March 1st, 2024. For 2 days, the response was the same loop it had always been. Then, on March 3rd, a section of the data stream changed. It was not readable in the normal sense, but it was different. The pattern had broken. The FDS had received the command and done something other than recite its loop. It had started reporting. It took the engineering team a week to decode what they were looking at. By March 10th, they had a clear picture. The spacecraft had successfully, returned the full contents of its own memory to Earth. What they found when they laid that memory dump alongside the original design documents was a concentration of errors in one specific region, not scattered randomly across the storage, clustered. The kind of distribution you would expect if a single chip responsible for storing that region had stopped functioning. The FDS on Voyager 1 holds roughly 68 kilobytes of total memory. That is less than a single low-resolution photograph on a modern phone. Every byte of that memory is doing a job. Roughly 3% of it, approximately 2 kilobytes, had stopped behaving correctly. The errors were localized to a single chip. That chip had failed. 2 explanations were considered at JPL, and the team was careful not to settle on either definitively. The first was radiation damage. Voyager 1 is operating in the interstellar medium, which is saturated with cosmic rays, high-energy particles traveling at substantial fractions of the speed of light, originating from supernovae, pulsars, and other energetic events throughout the galaxy. When a sufficiently energetic particle passes through a piece of semiconductor material, it can damage the crystal structure, flip the state of a stored bit, or destroy a transistor junction entirely. This failure mode is known as a single event upset, and it is one of the primary engineering challenges in designing electronics for space environments. The spacecraft industry has developed radiation-hardened components specifically to resist it. Voyager 1's hardware predates that discipline by about a decade. It was designed to survive the radiation environment of the solar system, not the interstellar medium. Nobody expected it to operate where it eventually ended up. The second explanation was simpler. The chip was 46 years old. It had been operating continuously, in vacuum, at low temperature, in conditions its designers never tested for longer than most of the people working on the recovery had been alive. Electronics wear out, transistors degrade, materials develop microscopic fractures, insulation fails. The fact that Voyager 1 had operated for 4.5 decades without a chip-level failure of this severity was itself extraordinary. Eventually, the odds caught up. Either explanation was sufficient. Both might have been true simultaneously. What mattered was that the chip was not going to be repaired in any conventional sense. Voyager 1 is not accessible. There is no service mission. Whatever had happened inside that chip was permanent. So the team had to do something that has few precedents in the history of space exploration. They had to relocate code, the routines that had been stored on the dead chip, the instructions the FDS needed to package science and engineering data into the format the transmitter expected, still existed in the design documents. The team still knew what the code was supposed to say. The problem was that the memory location where it had lived was gone. The chip that had held it was dead. And the remaining memory on the FDS was already full, because 46 years of continuous operation had left no unused capacity anywhere in the system. To make room, the engineers had to delete. They went through the FDS memory looking for code that was no longer doing anything useful, and they found it in an unexpected place. Tucked into the flight data subsystem were routines written in the 1970s to manage Voyager 1's flyby of Jupiter. That flyby had happened in March 1979. The code had been sitting in active storage for 45 years. Unexecuted, unmodified, occupying space. It was deleted. A piece of software written to handle a single gravitational encounter with the largest planet in the solar system, surviving untouched for nearly half a century, was finally erased so that the spacecraft could survive a memory failure in interstellar space. The Jupiter code had outlived its mission by 4.5 decades. It spent those decades as dead weight that nobody had ever bothered to remove, until it became the only available space to save something more important. With room cleared, the team had to break the relocated code into fragments. The dead region of the FDS had been one contiguous block holding routines that called each other in precise sequences. The free space scattered through the surviving memory was not contiguous. It was distributed across the chip landscape in disconnected gaps of varying sizes. The code had to be cut to fit those gaps, each fragment stored separately, and every reference within the code and across the rest of the FDS memory had to be updated to point to the new locations. Every time one routine called another, the address in that call had to reflect the new position of the code being called. Get one pointer wrong, and the FDS would execute a jump to an address that now held something else, producing garbage output, a crash, or nothing at all. The first patch carried the code for packaging engineering data. It left the antenna at Canberra on April 18, 2024. It travelled at the speed of light for 22.5 hours, covering the distance from Earth to Voyager 1. The spacecraft processed it and ran the new code. On April 20th, the response arrived back at Earth. The engineering data stream was clean. The numbers were formatted correctly. For the first time since November 14th, 2023, the team at JPL could read what their spacecraft was doing. The temperatures were within normal range. The power was holding. The instruments were operational and waiting for instructions. It had taken 5 months and a considerable amount of mathematical archaeology on decades-old design documents. To get there, the science data took longer. Each instrument's data packaging routine needed its own patch, its own fragment locations, its own pointer updates. The team worked through them systematically through May and into June. On June 13, 2024, the last of the 4 still active science instruments came back online. Voyager 1 was transmitting usable science again. The plasma wave subsystem was recording the hum again. The mission, against what seemed like reasonable odds, had not ended. But what happened next raises questions that no amount of engineering ingenuity can fully defer. Both the discovery and the breakdown had lived in the same machine. The instrument that Stella Ocker used to find the persistent plasma hum was the same instrument whose data packaging routines the team spent months relocating around a dead chip. The signal that revealed the texture of interstellar space and the signal that stopped making sense in November 2023 were both products of the same hardware, processed by the same software, dependent on the same ancient circuitry. Put those two things next to each other and a particular kind of discomfort becomes visible. We are hearing interstellar space more clearly than at any point in human history through a machine that is actively failing. Voyager 1 runs on a radioisotope thermoelectric generator. It is a device that converts heat from the decay of plutonium-238 into electricity. The design is elegant and has no moving parts. Radioactive decay produces heat. Heat flows through thermoelectric junctions, producing a voltage. That voltage powers the spacecraft. As long as the plutonium keeps decaying, there is power. The problem is that plutonium-238 has a half-life of approximately 88 years, which means it produces slightly less heat every day, which means slightly less electricity every day. The slope is shallow, but it is constant and relentless. Voyager 1 loses roughly 4 watts of generating capacity every year. After nearly 5 decades of operation, the spacecraft has less than half the power it launched with. The margins are now thin enough that an unexpected power draw, from a heater activating automatically or a sensor cycling through a diagnostic routine, can trigger automatic shutdown of lower priority systems to protect the ones that matter. Managing the power budget of Voyager 1 in its current state is a constrained optimization problem with consequences. Every watt is allocated deliberately. Every system that draws current is weighed against what it contributes to the mission versus what it costs. Over the past several years, instruments that were once central to Voyager 1's science mission have been shut down one by one, sacrificed to preserve the most valuable remaining capabilities as long as possible. The cosmic ray subsystem, which had helped confirm the Heliopause crossing in 2012 by measuring the flux of galactic cosmic rays, was shut down on February 25, 2025. The low-energy charged particle instrument, which had been measuring ions and electrons in the interstellar medium since launch in 1977, was shut down on April 17, 2026. The team did not want to shut them off. They had no choice. The thruster situation is its own separate deterioration. The small jets that keep Voyager 1 pointed at Earth have been accumulating residue in their fuel lines for decades, slowly narrowing the passages and reducing their effectiveness. The backup roll thrusters, which the probe had been using since 2004, were approaching the point of complete blockage. The primary thrusters that the spacecraft used originally had not been fired since 2004, when the backup system was switched in. By 2025, the engineering team faced the prospect of losing attitude control entirely, which would mean losing the ability to point the antenna at Earth, which would effectively end the mission. Their solution was to reactivate the primary thrusters. The heaters that feed those thrusters had been off for 21 years. The propulsion lines were cold and stiff. Firing them after that dormancy carried real risk. If something went wrong, the force of the firing could damage the spacecraft in ways that nothing subsequent could fix. Todd Barber, the mission's propulsion lead at JPL, called the successful March 2025 test a miracle save. The primary thrusters worked. The spacecraft regained reliable attitude control. The antenna stayed pointed at Earth. These two crises, the memory failure and the thruster deterioration, arriving within 2 years of each other after 4 decades of relatively stable operation, suggest that the probability of further hardware failures is increasing as the spacecraft ages. The components that have held on this long are the ones that got through the most dangerous part of their operational envelope. The ones still running are now beyond any design specification, operating in conditions no engineering test ever simulated, kept alive by improvised solutions, and the institutional memory of a team that has been maintaining the same spacecraft for nearly 50 years. What is still operating is remarkable to enumerate. The plasma wave subsystem is still recording the interstellar medium. The magnetometer is still measuring the magnetic field. These are the 2 remaining active science instruments. The transmitter is still broadcasting. The computers are still running. The attitude control system, after the thruster repair, is still keeping the antenna pointed home. Every reading that arrives at the Deep Space Network dish in Canberra is, by any reasonable engineering standard, a bonus. The spacecraft was designed for a 5-year mission. It has been operating for nearly 50. Every additional measurement is data that the designers of 1977 never expected to produce. And each of those measurements is arriving through a chain of components that is one unexpected failure away from permanent silence. In November 2026, approximately 1 year from now, at the time this analysis was written, Voyager 1 will cross a threshold that no human-built object has ever reached. It will be 1 full light day from Earth. 1 light day is the distance light travels in 24 hours, approximately 25.9 billion kilometers. A signal sent from the spacecraft at that moment will spend an entire 24 hours traveling home. A command sent in response will spend another 24 hours traveling out. 48 hours from one question to one answer. 2 full rotations of the Earth between the moment an engineer in Pasadena sends a command and the moment the spacecraft's response arrives. The Deep Space Network dishes in Canberra will track the signal through both of those days. The team at JPL will wait, and when the signal does arrive, it will carry whatever data the 2 remaining instruments have recorded in the interval. A real-time sample of the interstellar medium at a distance no probe has ever reached while still transmitting science. The plasma hum, the faint, persistent signal stellar ocker found in the archive in 2021, will still be there in that data. The oscillations of the interstellar medium do not care about the spacecraft's age or the state of its power budget. The medium was vibrating before Voyager 1 arrived. It will be vibrating after Voyager 1 falls silent. What the spacecraft does is provide a platform close enough and sensitive enough to hear it. That platform is running out of time. The JPL team has a plan internally referred to as the Big Bang. It involves switching off multiple heaters simultaneously, replacing their thermal management functions with lower power alternatives in a coordinated single operation. The goal being to recover enough power budget to extend science operations by 1 to 2 additional years beyond current projections. The plan is complex and carries risks because heaters are not neutral components. They maintain temperatures in systems that need to stay within operational ranges to function. Turning them off without replacement means accepting some thermal risk in exchange for power gain. The team believes the trade is worth making. After the Big Bang, the projections become increasingly uncertain. At some point in the early 2030s, on current trajectories, the power budget will drop below the minimum required to operate any science instrument. At that point, the carrier signal, the basic radio tone from the transmitter, may continue for some additional period. The largest dishes in the Deep Space Network can detect the carrier even without data underneath it. The spacecraft will still be pointing at Earth, still transmitting, still moving through the interstellar medium. It just will not be reporting what it finds. Eventually, the pointing will drift beyond the ability of the thrusters to correct, or the power will drop below what the transmitter needs to broadcast at detectable strength, or a component will fail in a way that cannot be patched around, and the signal will weaken to below the noise floor of every dish on Earth. At that point, Voyager 1 will not stop. It will continue on the same trajectory it has been following for 50 years, accelerating gently through the interstellar medium at roughly 17 kilometers per second relative to the Sun. It will pass through the Oort cloud, the vast spherical shell of icy objects that marks the outermost gravitational reach of the solar system, sometime in the next several hundred years. It will take roughly 40,000 years to come close to another star, the red dwarf system, AC plus 79 degrees, 38888, though it will not approach that system closely. It will just drift by in the general direction. After that, the trajectory will carry it into the open galaxy. If nothing disturbs it, Voyager 1 will still exist in 1 billion years. The materials of which it is made, aluminum, steel, scientific instruments in various metallic and ceramic forms, will survive in the vacuum of interstellar space for geological timescales. It will be physically intact and silent and moving at a steady velocity through a galaxy that has changed enormously since it left. Attached to the spacecraft is a golden phonograph record containing sounds, music, greetings in 55 languages, and a map indicating the location of the solar system. The record was not designed to be practical. Its designers knew that the probability of Voyager 1 ever encountering another technological civilization was vanishingly small. They included it anyway. Carl Sagan, who led the record project, described it as a message in a bottle thrown into the cosmic ocean. The bottle is still moving. The particular relevance of that image now is not its romance. It is its precision. The bottle analogy captures something accurate about the asymmetry of what Voyager 1 represents. On one side of that asymmetry is the scale of the cosmos, indifferent, unbounded, unchanged by whether any small machine is moving through it. The interstellar medium was humming for billions of years before the spacecraft arrived. It will hum for billions of years after the spacecraft goes silent. The physics does not notice the probe. On the other side of the asymmetry is the probe itself, a collection of aluminum and silicon built by a species that has existed for roughly 300,000 years, on a planet that has existed for 4.5 billion years, in a galaxy that has existed for 13 billion years. The spacecraft represents a tiny fraction of a fraction of a fraction of the time and scale of the system it is moving through. And yet it is the thing doing the listening. The interstellar medium would be silent to us without it. Not because the medium was not vibrating, but because we would have no way to hear it. This is the genuine strangeness of the Voyager 1 story, not the chip failure, though that was a remarkable engineering crisis, and not the plasma hum, though that was a genuine scientific discovery. The strangeness is the relationship between the two. The chip that failed in November 2023 was part of a system that had been quietly accumulating data about interstellar space for over a decade. The engineers who spent 5 months rerouting code around a dead memory region did so in service of a mission that was returning information about the universe nobody had ever been in a position to collect before. The moment of breakdown and the moment of discovery were not separate stories. They were the same story. What you have, if you hold the whole arc together, is a machine that outlasted every prediction, reached a place nothing built by human hands had ever been, found something unexpected there, started failing in multiple simultaneous ways, had those failures diagnosed and partially repaired across a communication delay measured in days, and is now in the final years of active science operation, while still returning the only direct samples of interstellar space available to any instrument on Earth. The plasma wave subsystem, the instrument that detected Ocker's hum, is still running. As of mid-2026, it is one of 2 active science instruments. Its recordings are still arriving at Canberra. The hum is still there in the data. The texture of the interstellar medium is still being mapped, interval by interval, as the spacecraft moves farther from the solar system. Stella Ocker, who found that hum in the archive as a doctoral student, is now building on that dataset to characterize the turbulent structure of the interstellar medium at scales that no other instrument can resolve. The turbulence matters because it affects how cosmic rays propagate through the galaxy, how energy from stellar explosions gets distributed across interstellar distances, and how the medium itself evolves over time. Those are fundamental questions in astrophysics, and the only way to address them directly is with measurements from inside the medium. There is only one instrument inside this medium taking those measurements. The questions that will remain open when Voyager 1 finally goes silent are not small ones. Scientists do not yet understand in detail why the density of the interstellar medium varies at the scales that the plasma wave subsystem is measuring. The turbulence Ocker found has a structure, but the mechanisms that produce that structure, whether they are driven by stellar winds, supernova remnants, magnetic instabilities, or some combination, remain subjects of active research. The data from Voyager 1 helps constrain the models, but it cannot answer all of them, in part because one spacecraft at one location is a single measurement. Understanding the medium fully would require multiple measurements at multiple positions, which would require multiple spacecraft. None are currently heading in that direction. Voyager 2 is also in interstellar space, having crossed the Heliopause in November 2018, 6 years after Voyager 1. It is traveling in a different direction, roughly 30 degrees south of the ecliptic plane compared to Voyager 1's northward trajectory. Its plasma wave data provides a second sampling point, separated by tens of astronomical units from Voyager 1's track. The comparison between the two gives scientists some ability to distinguish local variations from broader structures in the medium. But the separation is still small on the scale of the galaxy, and the two probes are the only sources of this kind of direct measurement. When they go silent, the in situ sampling of the interstellar medium will stop. Any future mission intended to return to interstellar space would face challenges that make the original Voyager program look straightforward. The Voyagers reached the Heliopause by using gravitational assists from Jupiter and Saturn, essentially stealing energy from the planet's orbital motion to fling themselves outward at speeds their own rockets could never have achieved alone. That technique depends on the right planetary alignment, which comes around once every 175 years. The next opportunity is not imminent. Alternative propulsion concepts for interstellar precursor missions, including solar sails, laser propulsion systems, and nuclear pulse designs, exist on paper and in preliminary research, but none are close to flight readiness. Getting another probe to the position Voyager 1 currently occupies, more than 160 astronomical units from the Sun, and doing so within a human generation, would require a technology leap of substantial magnitude. This is why the engineers at JPL fight for every additional month of operation. Every measurement Voyager 1 makes now is unique. There is no backup dataset. There is no second source for what the plasma wave subsystem is recording. When the instrument goes silent, that particular view of the universe closes, and it is not clear when or whether it will open again. There is something in that situation that is worth sitting with, not for romantic reasons, but for scientific ones. The most detailed measurement of the space between the stars that humanity currently possesses is being made by a machine that weighs less than 1,000 kilograms, was launched on a rocket design that was already a decade old when it flew, and is running on less electrical power than a light bulb. The instrument's sensitivity that allowed Oka to detect the plasma hum was not the result of advanced technology. It was the result of proximity. The plasma wave subsystem is not particularly sophisticated by modern standards. It is just very close to what it is measuring, closer than any other instrument can get. That proximity required 50 years of flight. The engineering that kept the spacecraft operational through a chip failure, thruster degradation, and the loss of multiple science instruments to power constraints is not the glamorous side of space exploration. It does not appear in history textbooks next to the launch images or the first photographs of Jupiter's moons. It is the long, quiet, meticulous work of keeping a conversation open across an incomprehensible distance, diagnosing failures through 45-hour communication delays, rerouting code around dead silicon using design documents from the Carter era, firing thrusters that had not operated in 21 years, and hoping they did not destroy the only probe in interstellar space. That work is ongoing. The team at JPL is still meeting regularly to manage Voyager 1's power budget, monitor its telemetry, plan future instrument shutdowns, and prepare for further contingencies. They are doing this for a spacecraft that launched before many of them were born, that has traveled farther than anything ever built by any civilization on this planet, and that is, by any reasonable projection, within a decade of its final transmission. What comes through when you examine this story carefully is a particular kind of tension. Not the dramatic tension of crisis and rescue, though that was present during the 5 months of the chip failure, a quieter tension, between the enormous scale of what the spacecraft is measuring and the fragility of the instrument making the measurement, between the vast impersonal patience of the interstellar medium, which has been oscillating for billions of years, and the finite, carefully managed operational life of the probe trying to record it. The universe is not going anywhere. The hum will continue. The turbulence will continue. The medium between the stars will go on being structured and textured and dynamic in the ways that Oka's analysis revealed, long after the last Voyager signal fades below the noise floor of every dish on Earth. What is finite is not the phenomenon. What is finite is our current ability to hear it directly. Right now, that ability still exists, somewhere 24 billion kilometers away. A spacecraft that launched in 1977 is still pointing its antenna at the pale blue dot it can no longer see. Its plasma wave subsystem is still recording the oscillations of the interstellar medium it moves through. Those recordings are still arriving at Canberra, riding a carrier wave that has been traveling continuously for nearly half a century, weakening as it covers the expanding distance but still, so far, above the detection threshold of the deep space network. Every day that signal arrives is a day we know something about interstellar space that we would not otherwise know. Every data point is a measurement that cannot be replicated from Earth, from orbit, or from any other instrument in the current roster of active spacecraft. Every transmission from Voyager 1 is, in the literal sense, irreplaceable. The strangest signal from Voyager 1 was not the memory loop of zeros and 377s that confused JPL for 5 months in 2023 and 2024. It was not the faint hum that Stella Ocker found in the quiet parts of an archive that nobody else had examined closely. Both of those signals were extraordinary for different reasons. The one that deserves the most attention is the one still arriving, the carrier wave that has not stopped since September 5th, 1977. The data stream that continues to carry information about a region of the universe nobody else can reach. The window is still open, briefly, and by diminishing margins, but open. That is the actual strangeness of this story. Not that a chip failed, though that was a remarkable piece of diagnosis and repair. Not that someone found a quiet signal in an archive everyone else ignored, though that was a genuine scientific discovery. The genuine strangeness is that we are here at all, listening to the space between the stars through a machine that should have stopped working decades ago, that we fixed from 15 billion miles away using code from the 1970s, that is running out of power on a shallow but inevitable slope. And that is still, for now, talking. The signal is still coming. To fully appreciate what Voyager 1 has accomplished and what its eventual silence will mean, it helps to step back further than the immediate story of the chip failure and the plasma hum. It helps to look at where this spacecraft came from, what decisions led to its creation, and why the particular combination of circumstances that put it in interstellar space was the result of events that will not repeat within any foreseeable timeframe. The 1970s were, in retrospect, a brief and unusual window in the history of space exploration. The Apollo program had demonstrated that sending hardware to another world was technically possible. The planetary science community was pressing hard for missions to the outer solar system. The space race, while winding down in some respects, had left an institutional infrastructure of engineers, mission designers, and deep space communication systems that was looking for new problems to solve. And the outer planets had just been calculated to be in an alignment that would not recur for 175 years. The alignment was crucial. Jupiter, Saturn, Uranus and Neptune are separated by enormous distances and each has a different orbital velocity. Normally, to visit all four with a single spacecraft would require propellant quantities far beyond what any rocket could carry. The gravitational slingshot technique changed that calculus entirely. If a spacecraft arrives at a planet from the right direction, the planet's orbital motion essentially throws it forward, adding velocity at no fuel cost. The energy comes from the planet itself, slowing the planet's orbit by an infinitesimally small amount while giving the spacecraft a potentially large velocity boost. By threading through the outer planets in the right sequence, a spacecraft could pick up enough velocity to reach the next one and repeat the process. The 1970s alignment meant that Jupiter, Saturn, Uranus, and Neptune were positioned such that a spacecraft launched in that specific window could use each planet to reach the next one. The window for the full Grand Tour, as the trajectory was called, was narrow. The Voyager program was scaled back from the Grand Tour design for budget reasons, and neither spacecraft was officially sent on the full trajectory. But the fundamental idea survived. Voyager 2, launched first on August 20th, 1977, eventually completed flybys of all four outer planets. Voyager 1, launched 17 days later on a faster trajectory, optimized for Jupiter and Saturn, was sent specifically to examine Titan, Saturn's largest moon, because Titan's thick atmosphere made it scientifically compelling enough to justify deviating from the path that would have allowed visits to Uranus and Neptune. The choice to prioritize Titan for Voyager 1 was a trade-off that had permanent consequences. Titan turned out to be extraordinary. It has a nitrogen-dominated atmosphere with surface pressure slightly higher than Earth's, rivers and lakes of liquid methane, and complex organic chemistry that makes it one of the most scientifically interesting objects in the solar system. The data Voyager 1 collected during its November 1980 flyby was worth the trade. But the trade meant that Voyager 1's post-Saturn trajectory was angled out of the ecliptic plane, the flat disk in which the planets orbit, more steeply than Voyager 2's. As a result, Voyager 1 ended up on a different path through the outer heliosphere and crossed the Heliopause in a different region of sky, at a slightly different distance from the Sun, than Voyager 2 eventually would. These are not trivial differences. The heliosphere is not symmetric. The pressure of the interstellar medium pushes on it from outside, creating a structure with a blunt nose on the upstream side, where the Sun's motion through the galaxy compresses the boundary inward, and an extended tail on the downstream side, stretched out in the direction the solar system is moving away from. Voyager 1 crossed the Heliopause on the upstream side, or close to it. Voyager 2 crossed in a region that may be slightly more compressed by the interstellar flow. Comparing their crossing distances, their plasma measurements, and their magnetic field readings gives scientists information about the asymmetry of the heliosphere that no single measurement point could provide. The fact that two probes crossed into interstellar space in different locations is scientifically valuable specifically because they were built to do different jobs. The deep space network that maintains communication with both spacecraft is itself a piece of engineering history worth examining. It was built in the 1960s specifically to support deep space missions, and it has been continuously upgraded and expanded since then. 3 primary stations are spaced roughly 120 degrees apart around the Earth at Canberra in Australia, Madrid in Spain, and Goldstone in California, so that at least one dish is always facing the relevant region of sky as the Earth rotates. The dishes at each site are among the largest steerable radio telescopes ever built. The primary dish at Canberra, the one used most often for Voyager 1 because of where the spacecraft is positioned in the sky, has a diameter of 70 meters. That is a reflector surface roughly the size of a sports stadium, aimed with sub-arc-second precision at a target 24 billion kilometers away. The signals arriving from Voyager 1 are extraordinarily weak. The spacecraft's transmitter operates at about 20 watts, which is less power than a standard incandescent light bulb. By the time those 20 watts have spread out over the roughly 24 billion kilometer distance, the energy flux arriving at Earth is vanishingly small. The Canberra dish can detect it only because the 70-meter reflector collects signal from a very large area and focuses it onto a sensitive receiver, and because the transmission is at a precisely known frequency, allowing the electronics to distinguish it from background noise. The entire power budget of the received signal is orders of magnitude below anything measurable by standard instruments. It is detectable only because its frequency is known in advance. This is part of why the November 2023 failure was so disorienting. The carrier frequency was still arriving at the expected strength. The basic transmission was intact. What was wrong was not the radio but the content. Distinguishing between a carrier wave with no data and a carrier wave with corrupted data requires decoding the transmission in detail, which the deep space network does automatically. The alarm was not an absence of signal, but a recognition that the signal contained something that did not decode correctly. The recovery effort that followed drew on one of the most unusual institutional resources in aerospace. Voyager 1 was built by a generation of engineers who worked at JPL in the 1970s. Many of those people are no longer alive. Some are retired and no longer in contact with the program. The documentation from that era, the technical specifications, the circuit diagrams, the software listings, the design decisions and their rationales exist in archives of varying completeness and accessibility. When the chip failed and the team needed to understand exactly what code had been stored on the dead region of the FDS, they were working with documents that were almost 50 years old, in formats designed for the computing technology of the 1970s, describing hardware that no longer exists in any production. Facility and software written in assembly language for a processor that has not been manufactured in decades. The fact that those documents were sufficient to enable the repair is itself a testament to the thoroughness of JPL's archival practices. Many institutions do not preserve their technical documentation at that level of detail across half a century. NASA's requirement for comprehensive documentation of space hardware, built up through painful lessons from earlier programs, made the repair possible. Without those archives, the chip failure might have been the end of the mission. There would have been no way to know what code the dead region was supposed to contain, and therefore no way to reconstruct it. The software itself is worth a moment of consideration. The flight data subsystem runs in assembly language. This is the lowest level of programming, where instructions correspond directly to processor operations, and the programmer specifies the exact memory address of every data item and instruction. There is no operating system managing memory allocation. There is no garbage collection, no dynamic memory management, none of the abstraction layers that make modern programming possible. Every byte of the 68 kilobytes of FDS memory is explicitly allocated to a specific purpose and accessible at a specific address. When a piece of code needs to call another piece of code, the call includes the literal memory address of the destination. This is why the chip failure cascaded into a system-wide communications breakdown. Every routine that called the dead region's code was jumping to an address that was no longer returning useful output, and this is why the repair required not just relocating the code, but updating every pointer that referenced it. In a modern software system, this kind of change would be handled automatically by a compiler, linker, or virtual machine. In assembly language running on a 1977 processor 24 billion kilometers away, it was done by hand, line by line, by engineers checking each reference against a table of old and new addresses. The fact that this was possible at all is a consequence of the simplicity and transparency of the system. Complex modern software, with its layers of abstraction, runtime environments, and dynamically linked libraries, would be far harder to patch under these conditions, precisely because it is harder to see exactly what is happening at each step. The primitive directness of assembly language on fixed hardware was, in this particular crisis, an advantage. What the Voyager program represents in the history of technology is a data point that receives insufficient attention. It demonstrates that hardware can survive in space for timescales that modern mission planning does not typically contemplate. Voyager 1 was designed for 5 years. It has operated for nearly 50. The limiting factors have not been catastrophic mechanical failure or unexpected environmental damage. They have been the gradual depletion of consumables, primarily the radioactive heat source, and the accumulation of wear in components that have no replacement mechanism. The spacecraft's basic architecture, its computers, its antennas, its structural frame, its instruments, has held together in interstellar vacuum for a period that would have seemed implausible to its designers. This has implications for how we think about designing future long-duration missions. The conventional approach to spacecraft reliability is redundancy, building multiple copies of each critical component and switching to backup systems when the primary fails. Voyager 1 used this approach, and the redundancy helped in several specific cases. But the most important factor in its longevity was not redundancy. It was the quality and durability of the original components, many of which have operated for decades beyond their specified design life without failing. The specific components that did fail, primarily the chip in 2023 and the thruster lines accumulating residue over several decades, were both predictable failure modes that could in principle have been designed against more aggressively, future missions intended for very long. Operational lifetimes would benefit from studying the Voyager failure modes in detail and incorporating lessons learned. The scientific return from those additional decades has been significant. Beyond the plasma hum that Oka discovered, Voyager 1's instruments have contributed to the understanding of the outer heliosphere in ways that were not anticipated when the mission was designed. The crossing of the termination shock, where the solar wind first slows to subsonic speeds, was observed and measured in detail. The structure of the helios sheath, the turbulent region between the termination shock and the heliopause, was sampled over a period of years as the spacecraft moved through it. The actual density and composition of the interstellar medium at the point of crossing was measured directly, providing ground truth for models that had previously relied on indirect observations. None of these measurements could have been made any other way. There is no substitute for being there. Telescopes can observe the heliosphere from Earth using ultraviolet and X-ray emissions, but those observations are averaged over large volumes and cannot resolve the fine structure that in situ measurements reveal. Computer simulations of the heliosphere have become sophisticated over the decades, but they are constrained by observational data to check against. Every new measurement from Voyager 1 has been used to test and refine models. And every refinement has changed predictions in ways that subsequent measurements have either confirmed or further modified. The heliosphere, it turns out, is considerably more dynamic and complex than the relatively simple bubble in a uniform medium picture that prevailed through most of the 20th century. The interstellar medium is not uniform. It has its own structure, its own turbulence, its own variations in density and magnetic field strength that change the shape of the heliosphere in response. The heliosphere itself has asymmetries driven by both the sun's motion through the galaxy and the non-uniform structure of the surrounding medium. The nose of the heliosphere, facing the direction of solar motion through the galaxy, is blunter and closer to the sun than early models predicted. The tail extends far downstream, but its structure is complex and not yet fully characterized. Understanding the heliosphere matters for several reasons that go beyond pure scientific curiosity. The heliosphere is a shield. Galactic cosmic rays, the high-energy particles that fill the interstellar medium, are partially deflected and slowed by the heliosphere's magnetic structure before they reach the inner solar system. The degree of shielding depends on the structure of the heliosphere, which in turn depends on solar activity. During periods of low solar activity, the heliosphere is somewhat less effective as a shield, and cosmic ray fluxes at Earth increase. This is a known phenomenon, documented over multiple solar cycles. Understanding how the heliosphere responds to changes in the sun's output, and how the interstellar medium's structure affects that response, is relevant to understanding the radiation environment in which life on Earth has evolved, and in which any future space explorers would need to operate. Beyond the practical shielding function, the heliosphere is interesting as a model system for stellar astrospheres in general. Every star has its own astrosphere, a bubble inflated by its stellar wind against the surrounding interstellar medium. These structures are too distant and too faint to observe in detail from Earth in most cases. By studying our own heliosphere from the inside, scientists can develop models and intuitions that apply more broadly to how stars interact with the medium between them. Voyager 1's measurements are therefore relevant not just to solar physics but to the general question of how stars modify their local environment. The interstellar medium itself is a subject of ongoing research that predates the Voyager program and will continue long after it ends. The medium is not static. It is swept by shock waves from supernovae, heated by ultraviolet radiation from hot young stars, cooled by the radiation of molecular gases in dense clouds, and stirred by the differential rotation of the galaxy. It exists in multiple phases simultaneously, with regions of cold dense gas, warm diffuse gas, and hot ionized gas all present at different locations and in different proportions. The region of the medium that Voyager 1 is currently traversing, a part of the local interstellar cloud, has its own particular characteristics, including a warm, partly ionized plasma with a composition and temperature that have been estimated through indirect means but never directly sampled until Voyager 1 arrived. The persistent hum that Ocker found in the data is a direct measurement of the electron density in that cloud. The electron density matters because electrons, being charged particles, interact with electromagnetic radiation and affect how light and radio waves propagate through the medium. Understanding the electron density of the local cloud helps calibrate measurements of more distant objects, because all observations of objects beyond the cloud are affected by the medium in between. The cloud's density also tells scientists something about the thermal state of the gas and the processes, maintaining it against cooling and recombination. These are specialized questions that matter primarily to researchers studying the structure and evolution of the interstellar medium, but they connect to larger questions about the galaxy's history and the conditions that produce the solar system. The local interstellar cloud and the broader structure called the local bubble that surrounds the solar neighborhood are thought to be remnants of ancient supernova activity. The local bubble is an enormous region of hot, low-density plasma, roughly 1,000 light-years across, surrounded by denser shells of gas and dust. The solar system is currently inside this bubble and has been for several million years. The bubble was probably excavated by a series of supernovae that occurred in the Sco-Sen Association, a group of young, massive stars that passed near the solar neighborhood in the geological past. Understanding the structure and properties of this region connects solar system history to the star formation history of the local galaxy, Voyager. One's measurements are one data point in this much larger picture, a single sample of one small region of one cloud inside one bubble in one arm of one galaxy, but it is a sample that could not be obtained any other way. In the hierarchy of scientific instrumentation, there is a fundamental distinction between remote sensing and in situ measurement. Remote sensing, observing something from a distance using radiation that travels from it to you, is powerful and versatile, but always involves interpretation. What you measure is not the thing itself, but the light or radio waves it has emitted or scattered or absorbed, and translating those measurements into properties of the object requires models and assumptions. In situ measurement eliminates most of those intermediary steps. You are where the thing is. Your instrument is directly interacting with the phenomenon. The data is as direct as physical measurement gets. For the interstellar medium, in situ measurement was not possible until 2012. Before that year, every measurement was remote sensing. Every model was constrained only by observations made from inside the heliosphere, and the medium itself was characterized primarily by inference and theory. The Voyager crossings changed that. The interstellar medium went from being something inferred to something measured. The difference is not academic. Consider an analogy. For most of human history, knowledge of the deep ocean was limited to what could be deduced from surface observations, from things that washed up on shores, from samples brought up by fishing nets, from the behavior of ships at sea. The deep ocean was real. Its existence was not in doubt, but its actual nature was largely unknown. The first deep-sea expeditions in the late 19th century revealed an environment utterly different from what had been expected, including abyssal plains, underwater mountain ranges, bizarre creatures adapted to extreme pressure and darkness, and hydrothermal vent ecosystems that operated on principles completely unlike surface ecology. None of that was predictable from surface observations. Voyager 1 is the equivalent of the first instrument to descend to the deep ocean. It has found that the interstellar medium has structure and turbulence at scales that were not resolvable from inside the heliosphere. It has measured a persistent hum that was not detectable from Earth. It has sampled a plasma composition and density that differ from predictions in ways that are still being analyzed. The interstellar medium is not a surprise in the way the deep ocean was a surprise. Its basic nature was understood in broad outline from remote sensing. But the details are different from the models, and details in physics have a way of being important. The question of what happens to all of this scientific infrastructure when Voyager 1 and Voyager 2 eventually go silent is one that the planetary science community has been grappling with for years. Several mission concepts for interstellar precursor probes have been developed and proposed over the past 2 decades. The innovative Interstellar Explorer concept proposed in the early 2000s would have used a Jupiter gravity assist and a solar sail or nuclear electric propulsion to reach the boundary of the heliosphere in 50 years, faster than Voyager 1 managed it. The interstellar probe concept, which NASA studied in detail in the 2010 timeframe, proposed a mission that could reach 200 astronomical units within 15 years using advanced propulsion. Neither of these missions was funded. The fundamental challenge is propulsion. Reaching the distances Voyager 1 has reached in a scientifically useful timeframe, meaning on a scale relevant to human careers and funding cycles, requires either very fast travel or acceptance of very long mission durations. Voyager 1 took 35 years to reach the Heliopause. A mission designed to reach the same distance in 10 years would need to travel roughly 3.5 times faster. Voyager 1's speed at launch was largely a gift from the Jupiter and Saturn gravity assists. To achieve comparable or higher speeds without relying on those specific planetary alignments requires propulsion technologies not currently available for flight, including advanced nuclear thermal or nuclear electric systems, or unconventional approaches like laser propulsion that are still in early research stages. There are proposals, primarily from the Breakthrough Starshot initiative, for small laser-propelled probes that could theoretically reach nearby stars within human lifetimes. Those concepts involve gram-scale spacecraft accelerated by ground-based lasers to a substantial fraction of the speed of light. They are designed for speed, not for scientific payload capacity. A gram-scale spacecraft cannot carry the kind of plasma wave system, magnetometer, or cosmic ray detector that Voyager 1 uses, and traveling so fast through the heliosphere and interstellar medium would provide only momentary glimpses of the environment rather than the extended in situ sampling that Voyager 1's relatively slow transit enables. The science that Voyager 1 is doing requires time on site. It requires a probe that moves slowly enough through the medium to sample it over distances that reveal structure. It requires enough power to operate sensitive instruments for months and years. It requires a communication system capable of sending data back across tens of billions of kilometers. These requirements do not lend themselves to simple or cheap solutions. A mission that could replicate and extend what Voyager 1 is doing in interstellar space would be among the most technically challenging and expensive planetary science missions ever attempted. This is the fundamental answer to the question of what comes next. The honest answer is that we do not know. We do not currently have the technology to do what needs to be done, and the missions that would develop or deploy that technology have not been funded. This is not a counsel of despair. Technologies develop, funding priorities change. The discovery of the interstellar medium's structure and the demonstration by Voyager, one that direct measurement is both possible and scientifically transformative, gives the scientific community a compelling case to make to funding agencies. But the timescales involved are long. If a mission were approved tomorrow, it would take years to design and build, and probably decades to reach interstellar space. The gap between Voyager 1's eventual silence and the next in situ measurements of the interstellar medium could easily be several decades, perhaps longer. During that gap, remote sensing will continue. The Hubble Space Telescope and its successors will continue observing the heliosphere from outside. Radio observatories will continue measuring the dispersion of pulsar signals through the interstellar medium, which provides indirect density estimates. Theoretical models will continue developing. The field will not be stationary. But there is something that remote sensing cannot provide, and that gap in the data will be real and acknowledged. The scientists currently working on Voyager 1's data are acutely aware of this. OCA's ongoing work on the turbulent structure of the local interstellar cloud is proceeding with some urgency, precisely because the dataset is finite and the window is closing. Every additional year of data from the plasma wave subsystem extends the baseline over which turbulence can be characterized. Every additional year narrows the uncertainties in the density structure. The work is happening in real time, with one eye on the science and one eye on the power projections. There is also a community of researchers working on complementary approaches, using the plasma wave data from Voyager 1 and 2 in combination with observations of dispersion in pulsar timing, with measurements of interstellar absorption lines in stellar spectra, and with satellite observations of the heliosphere's edges using energetic neutral atom imaging. The goal is to build a multidimensional picture of the local interstellar environment that is robust enough to survive the loss of in situ data when it comes. This is standard scientific practice, the kind of knowledge consolidation that happens whenever an instrument is known to be nearing its operational end. It is also an acknowledgement that what Voyager 1 provides is not redundant with anything else available. The deep space network that maintains contact with Voyager 1 is also facing its own evolution. The network has been upgrading its capabilities continuously since it was built. Newer, more sensitive receivers and more powerful transmitters have allowed communication with spacecraft at greater distances and with smaller power budgets than would have been possible in 1977. The network is also being supplemented by international partners, including agencies in Europe, Japan, and India, that have built or are building compatible deep space communication facilities. The combined capability of this international network will extend the range at which spacecraft can be tracked and communicated with, which means that the eventual loss of Voyager 1's signal, when it comes, will be heard by more ears than have ever listened to any spacecraft at this distance. The transmitter on Voyager 1 is not going to fail in a day. Its output will weaken gradually as the power budget declines and as the aging electronics introduce increasing signal noise. The precise moment when the signal drops below detectability is not predictable far in advance. It depends on the rate of power decline, on the success or failure of the Big Bang heater management plan, on whether any further unexpected failures occur, and on what the deep space network's sensitivity is at the time. Current estimates place the final end of meaningful communications somewhere in the early to mid-2030s. But these estimates carry significant uncertainty. The spacecraft could surprise its operators in either direction. What will not surprise anyone is the eventual outcome. Voyager 1 will go silent. When it does, it will be the first time since 1977 that there is no active signal from the spacecraft. It will also be the first time since 2012 that there are no direct measurements from inside the interstellar medium, and the first time since 2018 that both Voyager probes have simultaneously gone silent. The spacecraft will still exist, of course. It will still be moving. It will cross one light day from Earth sometime in November 2026, assuming the current trajectory holds, which it will. It will reach 2 light days in 2027 or 2028. A light year is about 63,000 astronomical units, and Voyager 1 is currently at roughly 160 astronomical units from the Sun, so it will take approximately 800 years to travel a single light year at its current speed. In 29,000 years or so, it will pass through the Oort cloud, the distant shell of cometary bodies that represents the outermost extent of solar gravitational influence. Long after any human civilization that now exists has transformed beyond recognition, a piece of hardware launched from Cape Canaveral in 1977 will still be moving through the galaxy. It will carry the golden record. The record contains greetings in 55 languages, sounds of Earth including thunder, waves, and birds, 116 images encoded as analog signals on the record's surface, and 90 minutes of music from various human cultures. It also contains instructions for how to decode it, on the assumption that any sufficiently advanced civilization encountering the record could figure out the encoding scheme from first principles. The record is gold-plated copper and is expected to remain physically intact for at least 1 billion years in the vacuum of interstellar space. Carl Sagan, who championed the inclusion of the record and helped design its contents, described the act of sending it as a statement of optimism about the universe, a declaration that intelligence is not so rare in the cosmos that contact is impossible, even if the probability of any specific probe being found is nearly zero. The record was not an engineering requirement. It was a choice. In the middle of a demanding and resource-constrained engineering program, a group of scientists and engineers chose to include something whose only purpose was to be found. Whether that optimism is warranted is one of the great open questions in science. The search for extraterrestrial intelligence, which began systematically in the 1960s with Frank Drake's Project Ozma and has continued in various forms since then, has not yet produced a confirmed detection. The absence of a signal, as the Voyager plasma wave story reminds us, does not mean the absence of a phenomenon. It means the threshold has not been crossed. What thresholds have not yet been crossed in the search for other technological civilizations is not known. The universe is large, and we have been listening for a very short time with instruments of limited sensitivity. The history of astronomy suggests that when we build more sensitive instruments and look more carefully at what we assumed was noise, we sometimes find something. The golden record, in this context, is not primarily a communication. It is a reminder. It reminds us, each time we think about it, that the question of whether intelligence is rare or common in the universe is open. It reminds us that the galaxy, despite being essentially empty by volume, contains structures and phenomena, and perhaps inhabitants that have not yet been measured directly. It reminds us that the absence of detection is not evidence of absence. The same reminder is embedded in the plasma hum story. For 5 years, scientists assumed the interstellar medium was too thin to produce a measurable continuous signal between solar shock events. Stella Ocker looked at what everyone else had called silence and found a signal that had been there the entire time. The lesson is not exotic. It is one of the oldest lessons in the philosophy of scientific inquiry. The universe does not make things obvious. You have to look carefully and at the right sensitivity and in the right format. And you have to be willing to examine the parts of the data that everyone else skipped. That lesson applies not only to the search for signals in archived data, it applies to the broader program of exploring the universe by sending instruments into it. We sent Voyager 1 to look at Jupiter and Saturn and their moons. We got the Galilean volcanoes, the ring structure of Saturn, the hazy orange clouds of Titan. Those were the results we were looking for. What we did not anticipate was that the spacecraft would still be functioning 30 years later, that it would cross into interstellar space, that the instruments originally designed for planetary observations would turn out to be sensitive to the subtle electromagnetic oscillations of the medium between the stars, and that a graduate student going through an overlooked archive would find in that data the first continuous measurement of the quiet voice of the local interstellar cloud. Science often works like that. The planned results are valuable. The unplanned results are sometimes more valuable. Voyager 1's planetary mission is finished. Its unplanned interstellar mission is ending. What it found in those unplanned years has changed what we know about the structure of the heliosphere, the nature of the interstellar medium, and the detectability of phenomena that were below anyone's threshold of expectation. The people who built Voyager 1 are mostly gone now. The people who launched it are retired or deceased. The original mission design team, the trajectory analysts who calculated the gravity assist sequence, the engineers who designed the instruments, the scientists who planned the observations, have been replaced by successive generations of researchers who are, in some cases, working with documentation they did not create, using software development practices that postdate the mission by decades, maintaining hardware they did not build and could not duplicate if they tried. What continues is the institutional commitment. JPL has maintained Voyager as an active mission for nearly 50 years, not because it was contractually required, but because the scientific return has justified the cost, and because there was, and still is, nothing else like it. The mission is a genuine one of a kind. The knowledge it is producing cannot be purchased, replicated, or otherwise obtained. As long as the spacecraft keeps transmitting and the data keeps coming, the mission continues to exist as one of the most cost-effective scientific programs in NASA's current portfolio, which is saying something given that the primary spacecraft was fully amortized before most of the current mission staff were born. The final chapter of that mission is being written now, in real time, one plasma measurement at a time, one power budget meeting at a time, one careful monitoring of thruster line pressures at a time. The end is approaching. The science continues until it does. There is a specific moment that the Voyager team and the broader planetary science community are watching for. Beyond the power budget milestones and the instrument shutdowns, it is a moment that has no exact predicted date, but a general time frame in the late 2020s or early 2030s. It is the moment when the signal-to-noise ratio of the incoming signal drops low enough that even the most sensitive receivers in the deep space network can no longer reliably extract the data stream. Before that point, the carrier wave may still be detectable as a tone without useful data. After it, Voyager 1 will effectively have become a ghost, still physically present and moving, but no longer visible to us. The engineering team has a name for this concept. They call it the noise floor. Everything above it is detectable. Everything below it is lost in the background. Voyager 1 has been moving toward the noise floor for decades as the power available to its transmitter slowly decreases, and the distance the signal must travel slowly increases. The rate of approach has been managed, slowed, and occasionally interrupted by technical interventions. The heater management plans, the instrument shutdowns, the thruster repairs, all of these are attempts to push the crossing of the noise floor further into the future. They will succeed for a while, perhaps until the early 2030s, perhaps a bit longer. Eventually they will not be enough, and the signal will fade. After that, the only connection between Voyager 1 and Earth will be mathematical. We will know its trajectory, we will know its speed, we will know where it was last measured, and in what direction, and at what velocity. We will be able to calculate where it is with high precision for centuries. The spacecraft will continue to exist in the universe in a precisely known location, silent beyond our reach, carrying its gold record and its 68 kilobytes of carefully patched memory and its 2 remaining instrument packages and all the accumulated miles of 47 years of continuous travel. What it will not be doing, after the signal fades, is listening. The plasma wave subsystem will still be there. The antennas will still extend from the spacecraft's body. The electronics will still exist. But without power to operate them, they will not be measuring anything. The interstellar medium will continue to oscillate around the probe, pressing its faint electromagnetic fingers against the antennas, inducing tiny voltages that nobody is recording. The universe will still be talking. We just will not be able to hear it. This is the situation we are in right now, before the signal fades. The universe is talking, and we have one instrument that can hear it, and that instrument is winding down. The window is open and narrowing. The hum is still arriving. Every day that passes is one day closer to the last day. Right now, at this moment, there is a dish in Canberra, Australia, pointed at a specific patch of sky in the northern constellation of Ophiuchus. It is collecting photons that left a spacecraft before the first personal computers were sold commercially. It is translating those photons into data that describes what the medium between the stars feels like to an antenna moving through it at 17 kilometers per second. That data is being downloaded to servers at JPL, where it will be analyzed by scientists who were children when the spacecraft crossed the Heliopause. The work continues, the signal continues, the questions continue. The universe has been waiting longer than we have existed to be heard, and we built a machine that could finally hear it, and that machine is still running, and the sound is still arriving. That is what makes this story strange, not in the sense of inexplicable or mysterious, but in the genuine sense of being outside normal expectations. We did not expect the spacecraft to survive this long. We did not expect it to cross into interstellar space while still returning science. We did not expect someone to find a continuous signal in the quiet between the storms. We did not expect to be able to fix a chip failure across 15 billion miles using code from the 1970s. All of these things happened anyway. Science has a word for results that fall outside the range of prior expectation. It calls them surprising. Voyager 1 has been surprising us for nearly 5 decades, and it is not done yet. If you find that kind of story worth following, then the right response is to pay attention to the science as it comes in. The next plasma wave paper from the Voyager team may describe turbulent structure at scales not yet characterized. The next power budget update may extend the mission by another year. The ongoing comparison between Voyager 1 and Voyager 2 measurements may reveal asymmetries in the heliosphere that current models do not predict. There is still science left in this mission. There is still data to be extracted, analyzed, and understood. The signal is still coming. The window is still open. The hum is still there. To understand the full weight of what Voyager 1 has accomplished, it is worth pausing to think about how we measure distance in space, because the numbers involved in this mission resist intuition in a way that demands deliberate effort. 1 astronomical unit, the distance from the Earth to the Sun, is approximately 150 million kilometers. It takes light about 8 minutes and 20 seconds to cross that distance. Mars, at its closest, is about 54 million kilometers from Earth, roughly 36% of 1 astronomical unit. The farthest planet, Neptune, orbits at an average of 30 astronomical units from the Sun, about 4.5 billion kilometers. When the Voyager 2 spacecraft made its Neptune flyby in August 1989, its signals were already taking 4 hours and 6 minutes to reach Earth. Voyager 1 is currently at approximately 160 astronomical units from the Sun. That is more than 5 times the distance to Neptune. Light, traveling at the ultimate speed limit of the universe, nearly 300,000 kilometers per second, takes over 22 hours to cross that distance. The spacecraft is so far away that even an electromagnetic signal traveling at the fastest possible speed in the universe spends nearly a full day getting from the spacecraft to Earth. And the spacecraft keeps moving. Every day, Voyager 1 travels roughly 1.47 million kilometers further from the Sun. That is over 17 kilometers per second, which is faster than any bullet ever fired, faster than any aircraft ever built, faster than the space shuttle was moving during its fastest orbital pass, and yet utterly negligible against the scale of the interstellar distances the probe has now entered. At this speed, reaching the nearest star system, Alpha Centauri, would take approximately 74,000 years. And Alpha Centauri is not even in the direction Voyager 1 is traveling. The spacecraft is heading toward the constellation Ophiuchus, the Serpent Bearer. There is nothing notable in that direction at any humanly relevant distance. No star planned for close approach, no target, just the interstellar medium, continuous and essentially uniform over stellar distances, with its layers of turbulence and its faint electromagnetic hum and its very occasional shock fronts from distant stellar explosions. This is worth naming directly. Voyager 1 is traveling to nowhere in particular. Its trajectory was not chosen for a destination. It was the natural result of the gravity assists it used to reach Jupiter and Saturn. The spacecraft left Saturn's gravity well on a path that happened to lead generally toward the galactic north, and it has been following that path ever since. There is no planned endpoint. There is no scheduled arrival. The spacecraft will travel through the interstellar medium for millions of years, passing through density variations, crossing regions of different temperatures and magnetic field strengths, moving through structures that no human will ever know anything about, because no instrument will be recording them, and no communication will be returning from that distance. In this respect, Voyager 1's operational life is a brief and sharply bounded episode within its physical existence. The spacecraft will exist for 1 billion years. It will be actively communicating with Earth for perhaps 5 more. That ratio, 5 years of voice out of 1 billion years of travel, is a reasonable measure of how thin the thread is that connects what we know about the interstellar medium to what we could know if we had better instruments and better access. The comparative thinness of that thread is not just an abstract concern. It has practical implications for some of the largest questions in planetary science. One of those questions is whether the solar system's current position within the local interstellar cloud represents typical conditions for the heliosphere, or whether the heliosphere's structure and shielding properties have varied significantly over geological time as the solar system moved through different regions of the galaxy over the past several billion years. The solar system has completed roughly 20 orbits of the galactic center. During those orbits, it has passed through denser regions of the galaxy, through spiral arm crossings with higher stellar density and more intense cosmic ray fields, and through regions of the galactic disk with different compositions and temperatures. The local bubble in which the solar system currently resides, that large, low-density region believed to have been carved out by ancient supernovae, is not representative of the entire galaxy. The heliosphere's structure in denser regions of the galactic disk would be different from what Voyager 1 is currently sampling. Perhaps significantly different. There is a hypothesis in the astrobiological literature that connects these galactic-scale variations to the history of life on Earth. The idea is that when the solar system passes through denser regions of the galactic disk, the heliosphere is compressed. Cosmic ray fluxes at Earth increase, and the resulting increase in ionizing radiation could affect mutation rates, atmospheric chemistry, and climate. Some researchers have proposed connections between these galactic-scale cycles and periodic mass extinctions or major evolutionary transitions in the fossil record. The evidence for these connections is debated, and the causal mechanisms are not well established. But the basic physics, that denser interstellar environments compress the heliosphere and allow more cosmic rays to reach Earth, is sound, and it depends critically on understanding how the heliosphere responds to the properties of the surrounding medium. That understanding requires the kind of in situ measurements that only Voyager 1 can currently provide. Understanding the present heliosphere in detail gives scientists better tools for modeling the heliosphere in past and future environments. The density, temperature, and magnetic field strength of the local interstellar cloud, as measured by Voyager 1's instruments, can be varied in models to simulate different galactic environments and predict how the heliosphere would respond. This kind of modeling is only as good as the observational data used to validate it. Voyager 1's measurements are the most direct validation data available. There is a related question about the heliosphere's role in the origin and early evolution of life on Earth. The Sun was much more active in its youth, producing stronger ultraviolet radiation and a more energetic solar wind than it does today. The young heliosphere, powered by that more active Sun, may have been larger and more effective as a cosmic ray shield than the current heliosphere, or it may have been more turbulent and less stable. Understanding how heliospheric structure scales with stellar age and activity is relevant to assessing the habitability of planetary systems around stars at different evolutionary stages. If the heliosphere plays a significant role in protecting planetary surfaces from cosmic radiation, then understanding heliosphere physics is relevant to the broader search for habitable worlds. Voyager 1, in this context, is contributing to questions that extend far beyond its immediate measurements. The data it collects about one specific region of the local interstellar medium at one specific moment in solar system history is feeding into a much larger scientific framework that connects heliospheric physics, galactic ecology, planetary habitability, and the history of life on Earth. The spacecraft itself is a single data point, but the scientific infrastructure that has been built up around its measurements makes that data point enormously valuable. This is another reason why the loss of Voyager 1's signal will matter. It is not just that we lose one source of data, we lose the only source of data in a category, in situ measurements of the interstellar medium, that has implications for multiple interconnected fields of research. The replacement of that data source, when and if it happens, will require a mission of equivalent scope, and the scientific motivation for such a mission is partly built on what Voyager 1 has already found. The discoveries that the mission enabled, from the Heliopause crossing characterization to the persistent plasma hum, define what future measurements should look for and why they matter. The engineering community has also learned things from Voyager 1 that are relevant to future mission design, quite apart from the science. The demonstration that radioisotope thermoelectric generators can power spacecraft for nearly 50 years, degrading predictably but slowly, is a design reference for any mission planning for long-duration deep space operations. The experience of diagnosing and repairing hardware failures across extreme communication delays has produced institutional knowledge about how to structure mission operations for scenarios where conventional feedback loops are not available. The thruster restoration success is a data point about the survivability of propulsion systems under long-term dormancy in space. Each of these lessons is relevant to any future mission planning for extended interstellar precursor operations. There is also a quieter, less quantifiable lesson from the Voyager program that is worth stating. The spacecraft's continued operation past its original design lifetime is not primarily the result of redundant hardware or conservative design margins, though both of those contributed. It is primarily the result of a team that stayed engaged with the mission for decades, maintained the institutional knowledge needed to respond to unexpected situations, and made a series of creative engineering decisions under constraints that would have been impossible to anticipate at launch. The mission extension from 5 years to nearly 50 is a human achievement, as much as a technical one. The recovery from the chip failure in 2020, 3 and 2024 is the clearest demonstration of this. The success required engineers who understood assembly language programming practices from the 1970s, mission planners who could develop a repair strategy that would work within 45-hour communication delays, mathematicians who could recalculate memory pointer tables by hand, and managers who could maintain organizational coherence through 5 months of uncertain diagnosis and incremental repair. None of these skills is unusual individually. Combined, in this context, in service of this specific problem, they constituted something genuinely rare. The ability to fix a computer that nobody can touch, in a language nobody programs in anymore, across a communication delay measured in days, using design documents half a century old. This kind of capability does not maintain itself automatically. It requires investment in institutional memory, in documentation practices, in the retention of expertise that spans multiple generations of engineers, and in the willingness to keep funding a mission that produces results on timescales measured in decades rather than mission review cycles. The Voyager program has been sustained across multiple changes of presidential administration, multiple NASA budget cycles, and multiple shifts in the agency's strategic priorities. Its continued operation is, among other things, a demonstration that long-term scientific programs can survive the institutional and political pressures that tend to favor shorter horizon investments. The plasma hum discovery is a case study in what that sustained investment makes possible. The signal was present in the data from 2017 onward. The data was being archived. The plasma wave subsystem was still running, but nobody found the signal until 2021 because nobody had systematically gone through the quiet parts of the archive at sufficient sensitivity. It took a graduate student with the time and inclination to look carefully at what everyone else had skipped. That graduate student existed because Voyager 1 was still operating and still generating data worth analyzing. If the mission had been terminated at any point in the preceding decade, the signal might never have been found, because the data might never have been collected or preserved in a form accessible to a researcher years later. This is the argument for long-duration science. Missions that is hardest to make to funding committees, but easiest to justify in retrospect. You cannot predict which datasets will contain unexpected discoveries. You cannot design experiments around phenomena you have not yet conceptualized. You can only keep instruments running, keep archives accessible, and trust that people who look carefully at the data will find things that the people who collected it missed. Voyager 1 has validated that trust more than once. The heliosheath measurements in the years between the termination shock and the heliopause were full of surprises. The geometry of the crossing was different from model predictions. The magnetic field direction at the heliopause was not what the standard model had suggested. The interstellar magnetic field orientation inferred from the crossing was inconsistent with some versions of the local cloud structure model. Each of these surprises has driven revisions to theories of the outer heliosphere, and each revision has produced better predictions that can be tested by future observations or by reanalysis of existing data. The persistent plasma hum is the most recent in this series of surprises. It was not predicted. No model of the heliospheric crossing or the interstellar medium specified that a continuous low-frequency emission should be detectable at Voyager 1's location and sensitivity. The signal was found because someone looked for it without expecting to find anything, and found it anyway. The signal's properties, its frequency, its stability, its location dependence as the spacecraft moves, are now inputs to models of the interstellar electron density that will be used to interpret measurements of much more distant objects. For years after Voyager 1 goes silent, the story of Voyager 1 is therefore not only about one spacecraft. It is about what scientific programs look like when they are given enough time and consistent enough support to produce results that nobody planned for. It is about what happens when you send something to a place nobody has been and keep listening to what it reports even after everyone expects it to stop working. It is about the difference between the universe we predict and the universe we actually find when we go looking. The universe we predicted, before Voyager 1, had a heliosphere that was more symmetric and simpler than reality. It had an interstellar medium that was detectable only in bursts, with quiet gaps between them that contained nothing worth measuring. It had a boundary between the solar system and interstellar space that could only be approached, never crossed, by any instrument in our current inventory. Each of those predictions was wrong, not because the science behind them was bad, but because the instruments available to test them were not sensitive enough, not in the right places, not operating at the right thresholds. Voyager 1 fixed the instrument placement problem by being in the right place. It fixed the sensitivity problem by being operated carefully enough that a signal at the edge of detectability could be extracted from years of archived data. It fixed the threshold problem because someone was willing to look below the noise floor that everyone else had accepted as the limit. The strange signal from Voyager 1, the one the headlines got excited about in November 2023, was the broken telemetry. The real strange signal, the one that will matter more in 20 years, is the quiet hum that has been arriving continuously since 2017. Both signals came from the same spacecraft. Both required the spacecraft to still be running. Both required someone at JPL to be paying attention. The spacecraft is still running. The people at JPL are still paying attention. The signal is still arriving. There is science left in this mission, and there is time left to collect it. And both of those facts are less obvious and less guaranteed than they might seem. Every morning in Canberra, when the 70-meter dish at the Deep Space Network complex locks onto the frequency at which Voyager 1 transmits, it is performing an act of sustained attention that has continued unbroken for nearly half a century. The act is mundane in its physical details. Radio waves arrive, receivers amplify them, electronics decode them, computers record the decoded data. Scientists analyze the recordings, but the cumulative result of that sustained mundane attention, over 47 years and counting, is an understanding of the space between the stars that humanity simply did not have before and cannot get any other way, and will not be able to replace for decades after the signal finally fades. That signal is still arriving. The mission is still running. The hum is still there. It is worth considering what the interstellar medium actually is at a deeper physical level, because the word medium is deceptively neutral. It suggests something passive, an environment, a background against which things happen. The reality is considerably more dynamic, and understanding it changes how you hear the plasma hum. The interstellar medium is the material that fills the galaxy between stars. It is not nothing. It is not even a particularly good vacuum by the standards of what we can produce in a laboratory. It is a mix of gas, dust, magnetic fields, and energetic particles that together make up roughly 10 to 15% of the visible mass of the Milky Way galaxy. The rest is stars and compact objects. The interstellar medium is the raw material from which new stars form, the recycling bin into which old stars release their processed matter, and the medium through which the energy from stellar explosions propagates across galactic distances. At the location of Voyager 1, inside the local interstellar cloud, the medium consists primarily of partially ionized hydrogen and helium, with smaller amounts of heavier elements. The temperature is in the range of a few thousand Kelvin, which sounds hot, but corresponds to very low energy for individual particles, because the density is so low. The density itself is roughly 1/10 of a particle per cubic centimeter, meaning that in the volume of a standard sugar cube, there are perhaps 10,000 particles. In the air around you right now, that same volume contains about 27 quadrillion molecules. The local interstellar cloud is, by earthly standards, an extraordinarily tenuous place. And yet this tenuous material has structure. It has variations in density. It has turbulence. It has a magnetic field threading through it with a strength of roughly a few microgauss, which is millions of times weaker than the Earth's magnetic field, but still measurable. That magnetic field is not uniform. It has structure at multiple scales, from stellar distances down to scales below what any instrument can currently resolve. The turbulence in the medium cascades energy from large scales to small scales in a way that is mathematically similar to turbulence in fluids on Earth, governed by related physical principles, even though the medium is nothing like ordinary fluid. The plasma hum that Ocker detected is a signature of this turbulence. The narrowband electron plasma oscillation at the frequency she identified is a resonance phenomenon, a mode in which the electron density fluctuations in the local medium oscillate at a natural frequency determined by the local electron density. Think of it like the way a tuning fork produces a specific pitch because of its size and material. The interstellar plasma produces a specific frequency because of its electron density. By measuring that frequency, you can calculate the density. By measuring how the frequency changes as the spacecraft moves, you can map the density variations, the turbulence, the structure. The frequency Oka detected corresponds to an electron density in the range of roughly 0.05 to 1/10 of an electron per cubic centimeter, consistent with independent estimates of the local interstellar cloud's properties from other measurement techniques. The fact that the in situ measurement agrees with indirect estimates is itself scientifically significant. It validates the models used to derive those estimates. More importantly, it provides a baseline for continuous measurements as Voyager 1 moves through the medium, allowing the team to track density variations in real time rather than relying on model predictions. The physical mechanism producing the hum is worth explaining in a bit more detail because it illustrates something general about how plasma physics differs from ordinary gas dynamics. In a neutral gas, like the air in this room, if you push on a small region of the gas, you create a pressure wave that propagates outward at the speed of sound. The molecules collide with each other and transfer the pressure disturbance from one location to the next. In a plasma, which is a gas in which a significant fraction of the atoms are ionized, meaning electrons have been stripped from their nuclei, the situation is more complex. The charged particles interact not just through physical collisions, but through electromagnetic fields. When the electrons in a plasma are displaced from their equilibrium positions, the resulting charge separation creates an electric field that pulls the electrons back. This creates an oscillation. The electrons overshoot their equilibrium, create a field in the opposite direction, oscillate back, and so on. The frequency of this oscillation depends only on the electron density. This is the plasma frequency, also called the Langmuir frequency, after the physicist Irving Langmuir who first analyzed it. The plasma wave subsystem on Voyager 1 was designed to detect these oscillations. When a region of plasma is disturbed, whether by a solar shock wave or by some more subtle process, the resulting oscillations at the plasma frequency produce electromagnetic waves that the antennas can detect. The challenge is that in the quiet interstellar medium, the oscillations are not driven by dramatic shock events, but by the background turbulence of the medium itself, a gentler and less dramatic agitation that produces a weaker signal. That is why the hum was so hard to find. It required not a stronger instrument, but a more careful analyst. What the turbulence actually looks like in the local interstellar cloud, at the scales Voyager 1 can resolve, is a question that Oka and her collaborators are still working on. The preliminary analysis from the 2021 paper showed that the density variations followed a pattern consistent with magnetohydrodynamic turbulence, the kind of turbulence that occurs in magnetized plasmas. This is theoretically expected, but had not been confirmed by direct measurement at these scales. The implication is that the interstellar medium is turbulent at scales far smaller than what can be inferred from indirect observations, and that the energy cascade from large-scale structures to small-scale fluctuations extends down to distances of just a few astronomical units or even smaller. Understanding this turbulence cascade matters for several specific scientific problems. One of them is cosmic ray propagation. Cosmic rays, the high-energy particles that fill the interstellar medium, are charged particles that interact with the magnetic field as they travel. The path of a cosmic ray through the galaxy is not a straight line. It is a complicated random walk, deflected by magnetic field variations at every scale, from tens of light years down to individual field fluctuations. The rate at which cosmic rays diffuse through the galaxy and the efficiency with which they are scattered depends critically on the spectrum of magnetic turbulence, which is itself related to the turbulence of the plasma medium in which the magnetic field is embedded. If the turbulence extends to smaller scales than previously assumed, the cosmic ray diffusion coefficient is different from current models, which affects predictions for how cosmic rays propagate, how they reach Earth, and how their energy spectrum should look. Current measurements of the cosmic ray energy spectrum at Earth include features, kinks, bumps, and spectral breaks that are not fully explained by existing models. Some of these features may reflect properties of cosmic ray sources. Others may reflect the diffusion process during propagation. Disentangling the two requires better characterization of the interstellar medium's turbulence structure. Voyager 1's measurements directly constrain the turbulence spectrum at the location of the probe, which is the only in situ data point available. Another problem where the turbulence matters is pulsar timing. Pulsars are highly magnetized rotating neutron stars that emit beams of radio waves. When the beam sweeps past Earth, we detect a pulse, and the timing of those pulses is extraordinarily precise, stable to fractions of a microsecond over years of observation. This precision makes pulsars useful as natural clocks, and arrays of pulsars, called pulsar timing arrays, are being used to search for gravitational waves with frequencies too low for ground-based detectors like LIGO to detect. But the timing of pulsar signals is also affected by the electron density of the interstellar medium along the line of sight. As the electron density changes, the delay introduced by the medium changes, shifting the apparent arrival time of the pulse. This effect, called dispersion, must be calibrated out to use pulsars as gravitational wave detectors. Calibrating the dispersion requires knowing the electron density structure of the medium, including its turbulent variations on multiple scales. Voyager 1's measurements of the density. Turbulence at the probe's location provide one direct calibration point for these corrections. The plasma wave data is, therefore, not just interesting as a measurement of the local environment. It feeds directly into two of the most active areas of contemporary astrophysics research: the origin and propagation of cosmic rays and the search for gravitational waves using pulsar timing arrays. These connections are not always made explicit in discussions of the Voyager mission, because the natural narrative of the mission focuses on the spacecraft itself, its travel, its discoveries, its technical challenges. But the scientific value of the data extends well beyond the immediate story. Every measurement Voyager 1 makes is being incorporated into a broader scientific framework that will continue to develop for decades after the mission ends. The same is true of the technical lessons from the chip repair. The methodology developed by the JPL team for diagnosing hardware failures across extreme communication delays, extracting the fault location from a memory dump, breaking relocated code into fragments to fit available memory space, and updating pointer tables to maintain code coherence, is now documented in the mission literature. Future missions to the outer solar system or beyond will inherit those lessons. The approach used to fix Voyager 1's FDS in 2024 will inform how engineers design diagnostic protocols for the next generation of deep space probes, particularly those intended for the outer heliosphere or interstellar space, where communication delays approach or exceed 1 day. The thruster restoration story is similarly instructive. The fact that a thruster system dormant for 21 years could be successfully reactivated with careful preparation and testing tells engineers something important about the long-term storage properties of spacecraft propulsion components. It suggests that dormancy, under the right conditions, does not necessarily mean permanent degradation. Future missions planning for very long operational lifetimes, perhaps decades of cruise phase before reaching a distant target, can reference the Voyager thruster experience when designing their power, management, and component preservation strategies. These are narrow but genuinely useful pieces of knowledge that would not exist without the mission. They emerge from the specific circumstances of Voyager 1's situation and the specific engineering decisions made to address those circumstances. They are not the kind of knowledge you can generate from theory or simulation alone. They require actually building and flying hardware into the environment that produces the failure modes, and then managing those failure modes in real time. This is ultimately what space exploration is about at the most practical level. Not the grand discoveries, though those are real. Not the inspiring images, though those matter. The unglamorous, grinding practical knowledge that accumulates when you send hardware to difficult places and keep it running long enough to encounter the unexpected. Every mission that operates past its design lifetime, every repair that succeeds across impossible communication delays, every anomaly that gets diagnosed and resolved and documented, adds to a body of engineering knowledge that makes the next mission more capable. Voyager 1 has contributed more to that body of knowledge than almost any other mission, precisely because it has been operating in conditions no other mission has faced, for as long as no other mission has operated. It went where nothing had been before. It stayed longer than anyone expected. It found things nobody predicted. It broke in ways nobody planned for. It was fixed in ways nobody had previously attempted. And it is still going. The plasma hum is still arriving at Canberra. The signal from the spacecraft that found the hum is still strong enough to decode. The team at JPL is still tracking the power budget, monitoring the thruster pressures, planning for the next instrument shutdown, preparing for the day when the Big Bang heater management plan needs to be executed. The scientists who work with the data are still publishing papers, still building on Ocker's discovery, still using the continuous stream of measurements to characterize the structure of the local interstellar medium in more detail than any previous analysis has achieved. Somewhere out there, in the direction of the constellation of Heliopause, a machine weighing 815 kilograms and measuring 3.7 meters across its antenna dish is moving through the space between the stars at 17 kilometers per second. Its nuclear power source is generating less than 40 watts. Two of its science instruments are still taking measurements. Its transmitter is broadcasting at 20 watts on a frequency assigned to it in 1977. Its computers are running software written before the first personal computer was sold, patched around a dead chip using a technique invented in 2024, running correctly after a 5-month interruption that required the retrieval and relocation of code that had sat unused in active memory for 45 years. That is what is out there. Not a mystery, not an alien signal, not something inexplicable, something far more interesting than any of those things. The longest-running experiment in human engineering, still producing results, still surprising the people who built it, still telling us things about the universe that we could not know any other way. The signal is still coming. The window is still open. The hum is still there. And as long as it is, someone in Canberra is listening. There is one final dimension of this story that deserves attention, and it is the one that most directly connects what Voyager 1 is doing to the experience of the people watching or reading about it from Earth. We live in an era of extraordinary scientific instrumentation. The James Webb Space Telescope can resolve galaxies forming in the first few 100 million years after the Big Bang, looking back nearly 14 billion years to a time before our solar system existed. The Event Horizon Telescope can image the shadow of a black hole 55 million light-years away, with an angular resolution equivalent to reading the text on a coin placed on the surface of the Moon. LIGO can detect the merger of two neutron stars by measuring a change in length smaller than 1/10,000th of the diameter of a proton. These instruments are products of 21st century technology, built with modern materials, controlled by modern computers, launched or installed in the past decade. Voyager 1 is different in every dimension. It was built with 1970s technology. It runs software that predates the microcomputer revolution. Its total computing power is a fraction of what is contained in a single modern automobile key fob. Its power budget is smaller than the electricity consumed by a nightlight, and yet it is doing something that none of those 21st century instruments can do. It is there. It is in the interstellar medium. It is touching the thing it is measuring rather than observing it from across the galaxy. The superiority of in situ measurement over remote sensing is not a technology gap. It is a proximity gap. No matter how sensitive a telescope you build on Earth or in Earth orbit, it is still on this side of the heliopause. It is measuring the interstellar medium through the heliosphere, through everything in between, through every source of noise and confusion that the intervening medium introduces. Voyager 1 is on the other side of all of that. It is in the medium itself. The measurement is direct. This is why the plasma hum matters so much, and why the loss of Voyager 1's signal will matter so much. It is not just that we lose one data source. We lose the only category of data source that has ever been in interstellar space. We lose directness. We go back to inferring properties of the interstellar medium from observations made inside the heliosphere, from the behavior of radio signals from pulsars, from the absorption lines in stellar spectra, from the emission of energetic neutral atoms detected by spacecraft still inside the solar system. All of those techniques are valid and scientifically valuable, but they are not the same as being there. The people who will feel this loss most acutely are not the general public, who will move on to the next news cycle quickly enough. They are the researchers who work with the data, the team that processes the plasma wave measurements, the scientists building models of the local interstellar medium and using Voyager data to check them, the pulsar timing groups that use electron density measurements to calibrate their gravitational wave searches, the cosmic ray physicists who use the turbulence spectrum to model propagation. For these people, the end of the Voyager mission is not an abstraction. It is the closure of a data pipeline that their work depends on, with no clear replacement on the horizon. Some of them have already begun to describe what they do in terms that acknowledge the finite nature of the resource. Ocker's papers on the plasma hum do not assume that more data will always be available. They are structured to extract the maximum scientific value from the existing dataset, to establish the most robust possible characterization of the medium's density structure from what has been collected, knowing that the collection will end. This is the scientific equivalent of careful archival work, the practice of treating existing data as a finite and irreplaceable resource, rather than a continuously replenishable supply. Other researchers are working on complementary approaches, developing ways to constrain the interstellar electron density from inside the heliosphere by combining multiple indirect measurements in ways that reduce the uncertainty of each individual technique. These approaches will not replace in situ measurement, but they will help preserve the scientific continuity. Across the gap between Voyager 1's silence and whatever mission eventually follows it into interstellar space, the hope within the planetary science community is that the discoveries enabled by Voyager 1 will make the case for an interstellar precursor mission compelling enough to fund. The argument is straightforward. Voyager 1 found unexpected structure in the interstellar medium. It found a continuous signal that existed below the threshold of prior assumptions. It crossed a boundary that models had not fully predicted. All of these findings demonstrate that our understanding of the heliosphere and the interstellar medium remains incomplete, and that the most direct way to advance that understanding is to send another probe. The counterargument is cost and time. An interstellar precursor mission capable of reaching the Heliopause within 20 years would require propulsion technologies and power systems not yet available for flight. Developing those technologies requires investment. Making that investment requires a funding commitment that sustains across multiple decades and multiple shifts in political priority. This is the same institutional challenge that every long-duration space science program faces, amplified by the unusual timescales involved in reaching interstellar space. Whether that challenge will be met in time to maintain some continuity of interstellar measurement is uncertain. The probability depends on decisions being made now in funding agencies and scientific advisory committees and government budget processes about what questions deserve sustained support over decades. The Voyager program's track record is the strongest possible argument for why such questions can be answered with patience and long-term commitment. It is also, perhaps, the strongest possible argument for why they must be asked now, before the only instruments answering them go dark. The signal is still coming. Every day it continues is an opportunity to learn something new about the space between the stars. Every day it continues is also a reminder that this opportunity is finite, and that what replaces it, if anything, depends on choices we are making right now. The hum of the interstellar medium has been there for billions of years. We have been able to hear it directly for fewer than 10. The machine that lets us hear it has maybe 10 more years of operation ahead of it, and possibly fewer. When you put those numbers next to each other, the fraction of cosmic time during which humanity has had a direct measurement of interstellar space becomes almost too small to describe. We arrived at this capability very recently. We may lose it soon. What we do with the time in between is the question that the two signals from Voyager 1 are ultimately asking. If you find these questions compelling, and the science behind them worth following, then pay attention to the publications coming from the Voyager team and the broader heliospheric science community over the next few years. The data pipeline is still open. The discoveries are still happening. The mission is still running. If you want to understand what it means to reach the edge of the solar system and hear the sound of the space beyond it, and if you want to understand what it costs to maintain that kind of listening, then this is the story to follow. The hum is still there. The signal is still coming. The window is still open.